Galileo's theory of physics, which is mostly this equation, and then we'll see that it's very difficult to actually evaluate or give an empirical test for this theory of physics. The math is quite a lot harder, but we will ultimately do it by making an analogy to sequences. Now, it's usually at this point that someone would typically introduce calculus, but I'll actually show that you don't need calculus at this particular stage. But if you want to go farther, then it's much easier to start using calculus. So, Galileo's theory of physics. Unlike Aristotle, who said that the force is related to delta x, Galileo proposed, after demonstrating that Aristotle's theory doesn't stand up to empirical observation, hypothesized that force is related to delta v, the velocity, and that is related to the average acceleration. So let's be clear about what acceleration is. It is the rate of change of velocity. And the average acceleration is defined as the change in velocity over change in time. So for an example, suppose that we start our stopwatch at 5 seconds for whatever reason, just to give a little variety to our examples. And at that time, the velocity of an object is 10 meters per second. Now, 5 seconds later, which is to say when time is equal to 10 seconds, when the stopwatch shows 10 seconds, the velocity of the object is 10 meters per second. Well, we define the average velocity as delta v over delta t, so the final, which is 0 minus the initial, which is 10, gives us a total change in velocity of negative 10 meters per second. The time change is 5 seconds, and therefore the average acceleration over this time period is negative 2, and that just represents that it slowed down over this time period. So there's a description of acceleration. Now, let's think about what does this theory of physics predict, and how could we test whether it gets predictions right? Well, we need to sort of know where an object should be located at what time. But, how do we figure that out? When it was a constant velocity, right? Acceleration was 0. All we had to do was multiply velocity times time, and we would get the displacement, and we could, easily figure out at what time some object should be located where. But here, if the velocity is a constantly changing quantity throughout the motion, right? The acceleration is positive, so the velocity is always changing. Then how do we figure out the displacement? Another way to put the difficulty is that we're looking, what we know under constant force of gravity, basically free fall motion, is that we know that the change of the displacement is constant. But how do you analyze that, right? How do you get a prediction about where this thing will be located? Well, just as a sort of initial preview, let's make an analogy to sequences. I mean, if we had the arithmetic sequence 5, 7, 9, where everything is just changing by 2 and 2 and 2 and so on, we could view this as an object being located 5 meters away, and then 7, and then 9, and so on, so that this is like a constant velocity motion. Maybe we're taking the time change to be 2, or whatever we want. We could adjust appropriately, but this seems to be a good analogy for constant velocity. And in high school, you may recall a closed form formula for an arithmetic sequence, which is a sub n equals a sub 1, blah, 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 right? A sub 1 just refers to the first term, and a sub n refers to any term. So if I chose n is equal to 3, then I'd be talking about the third term, which is equal to 9 in this example. Now, d is the common difference in the high school version of the formula. I'm choosing to call that delta. So in this case, since delta is equal to 2, d is equal to 2. And so for this particular example, I could use the formula a sub n equals this, and we could plug into that formula to confirm that it's getting the right answers. So for instance, if we plug in 2, we should be getting a sub 2, right? plugging in 2 for n, not for a sub n, right? A lot of high school students make that mistake, thinking that when we plug in 2 for n, this becomes 2, but that's wrong. It becomes a sub 2, which is equal to 7. In any case, also here I replace n with 2, and then I compute, and you get, after computation, you find that the value is 7, just as it should be, right? A sub 2 is, we know, equal to 7. Now, we don't always want to just confirm what we already knew. The use of this formula is that you can find the value of terms in the sequence that are very far away. And rather than have to write out 100 different numbers, you could just plug into this formula and figure out the value. Well, if we could do a similar thing with sequences that have not a constant change, but a constant change in the change, what I call delta delta, right? So in this sequence, delta 1 is equal to 2, delta 2 is equal to 3, and so on. So delta delta is equal to 1 because the deltas are changing by a constant rate of 1 every time. This is kind of like having constant acceleration motion. And so if we could solve this, we might be able to solve the physics problem that we're trying to solve. And we'll start on that project in the next video.